Okay, so as we've already learned in the last lesson, I can't just add the radicands of radicals. I can't just subtract them in order to make equivalent radicals. It doesn't work like that. So adding or subtracting radicals cannot be accomplished by simply adding or subtracting the radicands. If I plug these into my calculator, well, in the first case, if I have 4 root 3 plus 5 root 3, does it equal 9 root 6? No, it's not the same thing. Does 3 root 6 plus 5 root 6 equal 8 times the square root of 6? Yes, it does. Does 8 root 5 minus the square root of 5 equal 7 root 5? Yes, it does. Does 10 root 11 minus 4 root 5 equal 6 root 6? No. Does 5 root 7 minus 3 root 7 plus 7 root 7 equal 9 root 7? Yes, it does. And does 2 in the cube root of 7 plus 6 in the square root of 7 equal 8 in the fifth root of 7? No, it does not. So, looking at what we have up on the top, what was the commonality for all the ones we actually could do? Well, radicals with the same index and radicands can be combined. Add or subtract the coefficients. If I think of it this way, if I said that for example 2 here, that the square root of 6 I was going to replace with x, because they're all the same value. Square root of 6 is the same each time. This would be the same as 3x plus 5x is equal to 8x, which I know would be true. So if I think of the radicals, as long as they're identical, same index, same radicand, as being just a variable because it represents the same number every single time, I would add or subtract them the same way that I would variables. So if that's true, if I have 4 root 10 and root 10, then I have 5 root 10s. If I have 5 root 3, take away 2 of the root 3s, then I'm left with 3 root 3s. 9 minus 4 is going to leave me with 1 root 2. If I have 8 root 6 and 2 root 6, the root 6s are the same, so I could think of those both as x's. And the root 5s and root 5s are both the same, so I could think of those both like they were y's. Well, 8 root 6 and 2 root 6 is going to give me 10 root 6s. Negative 4 root 5 and negative 4 root 5 is going to be minus 8 root 5. But I can't combine the root 6 and root 5s because they're not the same radical. 10 root x and 5 root x gives me 15 root x. And 3 minus 5 minus 1 root a's is going to leave me with negative 3 root a's. If I plug this in my calculator, the square root of 3 plus the square root of 48, or 5 and the square root of 3, that is true. If I put in 7 root 8 minus 2 root 50, and then I put in 4 root 2, they are equivalent. Does this appear to contradict the previous rules we had? Yes. they're combined, but they're not the same radical. Square root of 8 isn't the same as square root of 50. Square root of 3 is not the same as the square root of 48. But what happens if I simplify these radicals? Well, if I have 48, then I'm going to say that 48 can get split into 2 and 24, 2 and 12, 2 and 6, and 2 and 3. I have one set of 2's, two set of 2's, which means that this would be the same as 2 times 2 times the square root of 3, or root 3 plus 4 root 3, and that would give me 5 root 3. I can do the same thing with example 2. Now I have 2 of them I need to solve. I'm going to say that 8 is going to split up into 2 and 4 and 2 and 2. I'm going to say that 50 is going to split up into 2 and 25 and 5 and 5. And I see that I have a pair of 2's here and a 2 that's left inside. I have a pair of 5's and a 2 that's left inside. So this would actually be the same as I had the 7, I pulled out a 2, and I'm left with the square root of 2. Minus I had a 2, I pull out a 5, and I'm left with the 2. Or 14 root 2 minus 10 root 2. And this would equal 4 root 2. So, in order to add or subtract radicals, they must be able to be expressed as like radicals, which means they have to have the same radicand and the same index. I can always check if this is possible by simplifying the radicals as much as possible. So, for example 1, I'm going to take my 40 and I got to simplify it. 2 and 20, 2 and 10, 2 and 5. Take my 90, I'm going to simplify it. 2 and 45, 3 and 15, 3 and 5. I've got a pair here, got a pair here, and then I have the ones that are going to be left on the inside. Which means that this is going to be the same as 2 root 2 times 5 plus 3 root 2 times 5, which would be the same as 2 root 10 and 3 root 10, or 5 root 10. I'm going to do the same thing for B. I'm going to say that with example B, I'm going to start by simplifying these, and for the first one, I'm going to get 4 root 6. For the second one, it's going to be 2 root 6. And I'm left with 2 root 6's. In the last case, I'm going to start by simplifying all these. Well, 6 root 75 is going to be the same as 6 times 5 root 3 minus 3, and this is going to be times 4 root 3 when I simplify the radical, and plus 2 times 3 root 3 when I simplify this. So I have 30 root 3 minus 12 root 3 plus 6 root 3. I'm left with 24 root 3's. Now, even though I'm simplifying, it doesn't mean that they're always going to be like radicals. So, if I simplify the square root of 20, which we've done enough times before, the square root of 20 is going to be the same as 2 root 5. Square root of 18 is going to be 3 root 2. square root of 80 is going to be 4 root 5. And the square root of 98 is going to be 7 root 2. Now I can only combine the like terms. 5 and 5 can get combined. Root 2 and root 2 can get combined. Which means that this is going to be the same as negative 2 root 5s and 10 root 2s. For example, B, I'm going to do the same thing. So the first one, I have 3, and when I simplify the radical, the simplified form of this is going to be 2 root 7 minus 1/2 times square root of 128 is going to be the same as 8 root 2 minus 2 times, this is going to become 5 root 7, and plus 2, and this is going to become 3 root 7. Multiply them out. 3 times 2 is going to give me 6 root 7s. Half of 8 is going to be minus 4 root 2s, minus 10 root 7s, and plus 6 root 7s. And I can see that I have 3 root 7s that I can combine, and I only have one of the root 2s. So this is going to be equal to 2 root 7s minus 4 root 2. For the last question, we're going to look at some application. So it says, the diagram shows the metal support bolded for part of the bridge constructed on the side of a hill. The measurements are given in meters, so all this will be in meters. Determine the total length of metal needed to make the support. Well, I have 2 parts. I have this part here, which I can call X. I have this part here, which I'm going to call Y. Now these are both right angle triangles, so I'm solving for the hypotenuse, which is something that we've done before. I'm going to say that x squared is going to be the same as 4 squared plus 6 squared. This means that x squared is going to equal 16 plus 36. X squared is going to equal 52. So x would equal the square root of 52. And then I have to simplify that. And it's going to become 2 root 13 meters in a simplified form. For y, I'm going to do the same process. Y squared is going to equal 12 squared plus 8 squared. Y squared is going to equal 144 plus 64. Y squared is going to equal 208. So if y is equal to the square root of 208, then I can simplify that. Y is equal to 4 root 13 in meters. If it wants the total length of the support needed, then I need to combine these. So I'm going to say that the support is equal to x plus y, or 2 root 13 plus 4 root 13, which is going to give me 6 root 13 meters. There is my simplest form. If I do it as a decimal, then 6 times the square root of 13 is going to be 21 to the nearest tenth, 0.6 meters. And there's my answer.